Guess who's back? We're back! Yup! Still don't have a haircut. This is going to be my quarantine haircut. Today we are doing 5.8 natural logs and trigonometric equations. Very exciting stuff. So today we're finally going to look at this famous thing called the natural logarithm and the number e. So we all know pi is, super great. Pi is delicious. Yum! We know that's a famous number, but there's another famous number that we haven't talked about yet. And it's a weird one. It's tricky to explain because it's just nobody really understands. Like, we know where it comes from. We don't understand why it's out there in nature so much. So there's lots of ways to calculate it. You can look at this function and graph it and see what happens. So that's what I'm going to do. I'm going to show you what happens if you go and you graph this. As n gets really, really big, we get to this thing, we get to a certain number, 2.71, and that's rounded. So we get to this number and it's like, oh, okay, great. Well, let's take a look at it. The graph. So here's that graph of 1 plus 1 over n to the power of n. And you get this really funky curve. So on down here, this is going to be n. And as n gets really, really big, if I start clicking here, I don't know if you guys can see the y value, but it is getting close to 2.71. You got to get to a really, really big value before you get there. 2.713. We're getting there closer and closer to 2.718. It's an irrational number. So we call it e. We call this number e. And it is an irrational number, so it goes on forever and ever. We just rounded it right there. You can type it in on your calculator. You'll have a button that says e to the x. And you can see that number pop up. Again, where does it come from? Well, it turns out that lots of natural processes in nature actually use that number. So you'll see it in exponential growth or decay. We're going to look at the graph of it. It's pretty soon, and we're going to notice that, yeah, it's exponential. We're going to look at what happens when we use it as a log base. And the Swiss mathematician Euler actually popularized this number e. So back in the 1600s, can't quite remember, everyone was like, great, cool, but what's the point of it? And you know what? There really wasn't a lot of purpose to it until, I think, the 1800s or 1900s when Euler made it more popular. Started using it in calculations and stuff. Because it turns out that it's actually very useful in finance equations, radioactive decay equations, anything that has growth or decay, so like bacteria and stuff. Yeah, that's just the way it be sometimes. So I thought I would spend just one slide, just showing you a little bit about e. This is such a weird thing. Students are also asking why do we care about this number e? And the answer is, I don't really know. To be honest, it just comes up everywhere in nature is kind of why. So it's called the natural number. E is called the natural number. We've never looked at this, but if you graph it in something called the polar coordinate system, you get this thing called a logarithmic spiral. It looks really pretty, and that's cool. Well, now I probably have your attention. We see it all the time in nature. So if you whip some stuff in water really fast, you actually get a logarithmic spiral. And you can see it here, 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 here. And the guy with the beard, that's my favorite, woo! And then here's a bunch of pictures of nature that all have that logarithmic spiral. Shells, universes, or cosmos, geez, I don't know, I'm probably using all the wrong words, but we see it all over the place. And the answer is we don't really know why, okay? We don't know why, but there it is. A little bit of mystery for you. So, as far as we go, if we take this number e and we use it as a log base, we would write y equals log base e of x. Well, just like how log is base 10, you can simplify it as y equal log base 10. Euler decided that this was so freaking special that he was going to give it its own name and its own symbol. Okay, so if we have log in base e, we actually write it as ln, okay? That's called the natural logarithm. So ln and logs are related because ln x is log base e of x. That's the same way to write it, okay? We prefer to write it like this because it's so freaking special because it's out there in nature, so we write it like that. All right. All right, so you can use your calculator and you can type in ln of 10, and you're going to get, if you go do that, I'll give you a moment, Whoopsie daisy. Having some trouble with my paper. Okay, so if you type that in your calculator, you're going to get 2.302585, and it keeps going. Okay, prove it's correct using e. Well, if you go on your calculator and you write e to the power of ln 10, you will get 10. Okay, now this is an important property to remember here because these are inverses of each other. Okay, so if you go e to the power of its inverse, you will just get the argument. Okay, so maybe write that down. So a function raised to the power of its inverse gives us the argument. So that'll be an important property around ln and e, which are inverses of each other. Okay, so ln x and e to the x are inverses of each other. I've said it 20 times now. It's kind of like how 10 to the power of x and log, because it's base 10, are also inverses of each other, right? We know that this graph looks like this, and this graph looks like that, and they reflect over the line y equal x. Well, ln x and e to the x are going to be exactly the same. Now, what follows in your notes is sort of some extra reading, so I'm not going to go through this. If you want to do a bit more reading about ln x and e to the x, you can go read this, and I actually recommend this YouTube video. Okay, so it's in your note package. This is the title of the video, okay? And here's a link to it. You have fun typing it in, okay? Or you can try just going to YouTube and looking at the title. If you want to learn a little bit more about E, I think it's a 10-15 minute long video. It might clear up just some of the, like it's just like, why do we have E? Like what's so special about it? It might clear up that if you have that feeling. But otherwise, if you are okay just being like, all right, what do I need to know? I need to know that ln x is log base E, right? You need to know, hey, that's what that means. E is this special number, 2.71, okay? It's very special, it's called the natural log, and these things are inverses of each other. If you knew that, ding, you'd be doing just fine, just dandy, believe me. Okay, so I went ahead and I graphed y equals e to the power of x. Well, this looks exactly like our exponential functions, and of course, I'm not surprised, that's exactly what it is, because remember, e is just 2.71. So if you go 2.71 to the x, that would be very similar like as 2 to the x or 3 to the x, right? Which is just an increasing power function. So we have a horizontal asymptote. We have the y-intercept 0, 1. This isn't really that mysterious, okay? It's just, it's so special we gave it a special letter, okay? Once you get your brain around that, it's going to be okay. You'll lose all that anxiety. I also said I graphed y equal ln x. Well, it's a log graph. Of course it's a log graph because ln x is log base e, right? So it's just log in a weird base, 2.71. So of course it's exactly like any other log graph we've seen. Vertical asymptote at x equals 0, x-intercept at 1, 0, and just note the shape is the shape of a log graph. So yeah, they're inverses of each other. Great, this is going amazing. Okay, so a couple questions that you might get on the exam. They keep them pretty light if it even shows up. It does, in some capacity, show up on the exam. You just never know. You don't get a lot of questions on it. So it's like you might get one graph and then that's it. Or you might get one equation that has e to the x or something like that. Because they are basically just a special kind of log, right? So we can graph something like this using our what we know about transformations. Okay, so e to the x we know is just going to look like this, right? So there's y equals e to the x, and there's our y-intercept 0, 1. Well, what would happen if we shifted it up 2 units? Everything goes up. Oops, don't forget your horizontal asymptote at y equals 0. Okay, so if I'm shifting it up, this is shifting everything up 2 units. So now it would go to the point 3. And this, don't forget to also shift up your asymptote. It's going to go up 2 units. So new asymptote at y equal 2. And there it is. There's the graph of y equals e to the x plus 2. Well, that's easy peasy. What about this one? Well, it's a log graph. So just keep in mind that shape of a log graph that looks like this, that goes to the point 1, 0, and okay, it's ln, so what? This means that we're shifting everything 2 units to the left, so 2 units left, shifting everything that way, including our asymptote. Wunderbar! Excellent! Okay, so shift everything this way. Asymptote is now over here at the point x equal -2. This point is going to go over to 0 and then -1 rather. Okay, so you can label that -1, and we know it's going to have that same shape, and it's going to look something like this. Now, some of you guys might be wondering, well, what about the y-intercept? Well, we know the y-intercept is when x equals 0, so if you go pop that into your equation, you would get ln 0 plus 2, which is just 2. Now, they would never expect you to calculate that on the exam, but they would expect you maybe to label it as 0 ln 2. So when you're doing a sketch, remember, you don't need to have any grid lines. As long as you label everything, we're going to be happy with that. Okay? So there it is. You might have to do a little question like that, where you have to shift some stuff. That's really no big problem. Okay. Couple more conclusions that are going to be important for us. So our log background allows us to discover a very useful piece of information. Watch this. So we know that if we have log base 2 of 2 to the 3, the answer is 3. Let's check. Use the definition of a log. It would be the base raised to some power has to equal the argument, right? So same base, the answer is the exponent. So that makes sense. If we had log base 10, it would be the same thing, right? So this is log base 10, and it's raised to, if the argument's 10 to the 7, so the answer is 7. Why? Well, the base is 10, so 10 to some power equals the argument, 10 to the 7, so answer is 7. Well, what about these two things? Now remember, they are inverses of each other, so the answer is the exponent. Okay, they basically cancel each other out. There is another important conclusion. So this is important. If you have ln and the argument is e to some power, the answer is the power. Just like how when you have log base 10 and then 10 to the 7, the answer is 7. Over here, this is always going to be 1. You can type it in on your calculator if you like and check. The reason for it, of course, is because, well, think of this as being to the power of a. Right now, a is 1, right? I got ln e to the 1, so the answer is 1. Well, if I just kind of go general and say, let's just call the power a, okay? Well, I can rewrite ln. It is log base e, and then it's to the e to the a. Now we're in this same situation, okay? This and this match, so the answer is the exponent, right? Because you'd be asking yourself the question. You'd be saying, well, e to some power has to equal the argument, e to the a. What's the question mark? The question mark is whatever a is. In this case, a is 1, so the answer is 1. All right? So please remember this property. Very, very important. Because when it does come up on the exam, usually it has something to do with that property. Okay? Here, check your understanding. So if I say, hey, what is ln e to the 13? The answer is 13. It's whatever is in the exponent. If I said, hey, what is ln e to the power is the square root of 2. The answer is square root 2. Okay? You're doing just fine. Don't worry. Okay, so what else? Well, because ln is just a special form of log, all of our log laws, everything we know about solving equations applies to ln. So sometimes it just shows up on the exam in the capacity of, they give you a question instead of, I could rewrite this question using log, but they just say ln and they say, hey, expand this out. So let's do it. How would we do it? Well, we're going to be using our log laws, right? So we have a division. So that would be the division law, which means that it came from here, right? It used to be a subtraction, right? Then what? Well, we have product law here because we can write this one and this one separately. We know that we use addition when that's the case. This, the square root of z, can be written as a fractional exponent, so you can write it as z to the 1/2. Then what? We can use the power law to bring those all down. So this would be 2 ln x plus 3 ln y, subtract 1/2 ln z, and you're done. You've expanded it out. Now be careful on the exam. They like to give an expand question. Okay, so they might give this and say expand, or sometimes they give the question where they start here and they say write it using a single logarithm or something like that. All right, this one down here, well, just like this one. I'm so smart. Here we go, I had an example for it. So they might say, hey, write this using just one log. And it's ln, but we know those laws apply. So let's see, we can use power law. I'm going to be lazy and just bring that up there, and this 1/3, I'm going to bring it up here. Okay, so that would be my first step. The next step is now use product law, quotient law, all that stuff. So addition means that I can rewrite them as long as I write them multiplying together. So there's that one, and then I write subtract ln, what is it, x squared plus 2 to the 1/3. Now I have subtraction, so that is going to be the quotient law. So it's the first argument, so it's going to be ln, big bracket. First argument, x minus 1, x plus 3 to the power of 3, divided by second argument, x squared plus 2 raised to the power of 1/3. Done. It's ugly, but there it is. Some of you might be asking, like, do I need to rewrite this as a radical? And it's up to you. So if you want to write it as the cubic root, it's fine. Or you can leave it like that. What else have we got going on here? Right, we can solve equations. There's nothing new here. You can solve using regular log, or you can now solve using the natural log. Okay? So in a question like this is like one of the hardest varieties that we saw when we did this type. You're going to apply ln to both sides. So you can apply ln over here, and you can apply ln over here. There we go. Now it's like, okay, I got to solve for x. I got the quotient law here, or sorry, the product law. So I can rewrite it like that. Okay, on this side I can bring the x down in front using the power law. And I got to do the same thing over here. I need to bring this down in front. So I'm going to do my best to not write a bunch of stuff. Don't forget the brackets. There we are. Now what? Well, you're trying to solve for x. So isolate your x variables. Get everything that has an x over to that side and everything else over to that side. So I'm going to have to distribute this into the brackets. That'll be my first step. And now I am going to get a bit lazy and just say I'm not going to recopy that. So here we get plus x times ln 5 plus 4 ln 5. Now I'm going to move this to the other side. So we're going to see the sign flip to subtraction. So now I'm going to finally start rewriting this. You need a bit more room here. So we have x ln 3 subtract this x ln 5 equals ln 2 plus 4 ln 5. I just rewrote those two terms. Now it's like, okay, I can pull the x out here. That will leave me with ln 3 minus ln 5 equals all this stuff. Almost there. You can now divide both sides by this, right? So we'll do that. We'll just pretend I wrote it there. And you're going to get x equals this numerator, ln 2 plus 4 ln 5 divided by that stuff. There. And you can leave your answer like that. That is some kind of number. If you had a calculator, you could pop it in and get an answer. But we're not really interested in that. We're interested in, do you know the procedural steps, the algebra to get from here to there? Okay? And they very often have a question of this difficulty on the exam. So watch out for it. Do lots of practice. Watch my 10-minute maths. Yeah. All right. Well, what if you had one like this? Well, these are the variety where you need to either combine it down into one log, right, and then use exponential form. Now, which is what we're going to do. So let's move this over to this side. So you're going to get negative ln x equals 1. Now I can do quotient law. So first argument divided by the second one. And now I can use exponential form. But be careful. Remember, this is log in base e. Okay, so if it's more useful to you, think of it as log base e. So I'm going to say e to the power of 1 equals the argument. That's just using my log laws, right? My definition of a log. Now, I don't know what e to the 1 is. Well, yeah, I do. It's 2.71. You're just going to keep it like that. It's like pi. Okay, you never get rid of the pi. You keep it as an exact value. So I'm going to multiply both sides by x. And I'm going to get e times x equals x plus 1. Okay, then what? Well. I suppose, solve for x, so move this over here. So you're going to get e to the x minus x equals 1. Now, this is tricky. I'm not going to deny it is tricky. But you have an x common to both terms. So pull out the x. You would get e subtract 1 equals 1. Divide both sides by this. It's just a number. So you get x equals 1 over e minus 1. And remember, this is like 2.71, so it's kind of like having 1 divided by 1.71. But we leave it as an exact value. Boom! Done. Not gonna lie, like that's tricky. It's hard to look at. Yes. It's not fun to look at. Okay. Now, here's a place where we're going to use that special property that I was talking about before. So when you have a function raise to the power of its inverse, you're going to get the argument out. They're going to cancel. Okay? So that's what happens right here. You need to realize that. So if you need to write it again, a function raised to the power of its inverse yields the argument. The argument. Okay? So once you realize that, you're like, okay, so I have 2t minus 1 equals 5. Now you can solve for t. So move that over there. And you're going to get 2t equals 6. And wow. That's easy. Okay, so they'll give you a question like that where the math is really easy, but you need to remember maybe some important piece of information. This is going to be a question where you're going to use the other fact that we noticed. So we have an equation. Okay, now it's not obvious, but there's no way you're going to be able to solve this. You need to get the t somehow down out of the exponent. Well, one way you could do this is by applying ln to both sides. So apply ln to both sides. All right, and then you use that property of, hey, remember, when you have ln e, the answer is the exponent. Okay, so whatever is in the exponent is the answer. So it's 2t minus 1 equals ln 5. Add 1 to both sides. So you get ln 5 plus 1. Divide by 2. So you get t equals ln 5 plus 1 all divided by 2. And yeah, it's ugly, but it's an answer. So we are trucking along, just dandy. Oh, that's it. I don't have anything else for you guys. The homework. I'll post this. I'll post a link to that in the video description and also on Teams. So thanks for joining me. See you next time for the last lesson in the unit. Bye-bye.